As you consider the design of synthesis of an organic molecule, you should keep three key things in mind. One, the number of carbon atoms, which tells you whether or not you need to make carbon-carbon bonds. Two, the functional groups and their relationship to each other. And three, the stereochemistry. As you consider applying the addition reactions I've described in the videos in this playlist, the last two of these are important considerations. With respect to functional groups, you should be looking for the occurrence of two functional groups, a 1,2-diol, compounds that have hydroxyl groups on adjacent carbons, and molecules that have two carbonyl groups, indicate specific addition reactions that I've described in this video. Beyond that, if the molecule is a primary bromide, you can consider adding HBr to an alkene in an anti-Markovnikov way. And thirdly, there are stereochemical cues that suggest that syn addition has occurred to an alkene. Let's take a look at a few examples. Suppose the target molecule, the one you want to make, is an epoxide. I've shown specific stereochemistry here, so it needs to be made from a precursor that will give you that exact stereochemistry. In fact, because epoxides are made from alkenes, you simply need to choose an alkene that has methyl groups on the same side and the larger alkyl groups on the other side. I recommend writing the long carbon skeleton in exactly the same way. Put the double bond where the epoxide is, and then just be careful to put the alkyl groups on the correct sides of the double bond. As we finish our planning process, we need to talk about the reagents and conditions that will work for it. Alkenes are transformed into epoxides using peracids. Here's a target molecule that's an alkane, but it's a special one. It has specific stereochemistry. And notice that the alkyl groups are both pointing toward us, and the hydrogens on those stereogenic centers are pointing away from us. They can be added with syn addition if we pick the right alkene. As I suggested for planning the use of epoxidation, write the carbon skeleton in exactly the same orientation you have in the product. And again, make sure you put the two methyl groups that are shown on the same side toward us in the product on the same side of the alkene. So syn addition will make the stereochemistry you need. As we consider reagents, alkenes are reduced with syn addition using hydrogen gas and a metal such as platinum. Here's a target that's a 1,2-diol. We know how to make 1,2-diols from alkenes. The hydroxyl groups are added to the same side of the double bond with syn addition. I've written the long chain of this target molecule in the way that it's commonly written, with a zigzag chain. But it's not the best way to draw the structure to decide which alkene we need to have the stereochemistry I've shown here. So I recommend rewriting this diol, orienting the hydroxyl groups so that it's clear that they can be made from an alkene by syn addition. To redraw this molecule, I'm going to rotate the hydroxyl group up. This alkyl group will rotate toward us, and the hydrogen will rotate down and away from us. At the same time, I'll be rotating this hydroxyl group slightly up. That rotates the methyl down and rotates this one toward us. The rewritten structure looks like this. Now it's clear that the hydroxyl groups could be added to an alkene, drawn with the same orientation. The two larger alkyl groups toward us, and the methyl and hydrogen on the other side of the double bond. This alkene with the Z stereochemistry is the one we need to make the stereochemistry we want in the final product. What remains is to show the reagents for this reaction. Osmium tetroxide with an oxidizing agent such as N-methylmorpholine N-oxide works well. Here's a target that's a bit different. It has two carbonyl groups in the molecule. Dicarbonyl compounds, aldehydes and ketones, can be made by cleaving cyclic alkenes. We need to be careful to pick a ring size that works, that gives us the separation we need between the two carbonyl groups. In this case, there are 4 carbons between the two carbonyl groups, so we need a 6-membered ring. These 4 carbons, plus the 2 of the alkene double bond. To make sure we pick the right structure, I recommend rewriting this structure so we can very clearly see where the double bond will be. To rewrite the structure, I'm going to rotate around this single bond here. And I'm going to rotate this group up where it needs to be. Here's the rewritten structure. We still have 4 carbons separating the carbonyls. But now the carbonyls are oriented so we can clearly see where to put the double bond. This will be a 6-membered ring that looks like this. When the alkene double bond is cleaved by ozonolysis, we'll generate a ketone on the left-hand carbon and an aldehyde on the right-hand carbon, because there's a hydrogen here at that carbon atom. What remains is to write the specific reaction conditions. We'll first treat with ozone and then with a reducing agent. DMS, dimethyl sulfide, is both convenient and effective. And let me show you one more example. Take a look at this structure. We know we can make primary bromides by anti-Markovnikov addition to alkenes. So we need to use this structure, and we need to use HBr with peroxides added as the reagent conditions. So, in summary, it's pretty easy to see how to use the alkene addition reactions I've described in these videos if you focus on the occurrence of functional groups and focus on the stereochemistry.